Hello, everybody. In today's class, we will talk about the problem number 1 of 2021 December Platinum USACO competition, which is tickets. Before we start the class, let me remind you that today, tomorrow, and Monday is the first competition in 2022, USACO 2022, right? Please make sure you reserve enough time over this weekend to do the competition. Okay, that being said, let's start the explanation for problem number 1 of USACO Platinum 2021 December contest. The class, for people who hasn't attended the class before, the class goes like this. We review the problem, we talk about the algorithm, and I will give you a pseudocode on how to implement the algorithm. The homework is for you to implement the real code. We use C++. Let's look at the problem here. The problem basically goes like this. You have a set of checkpoints. Each checkpoint, you can buy certain ticket, right, at some price P. And this ticket allow you to go between checkpoint A and checkpoint B. Okay. So the question is, if you have a certain checkpoint, 1, 2, 3, all the way to N, what is the shortest cost for you to go to both 1 and to N? Right? For example, at 3, you may be able to buy a ticket, at some price, let's say $10, allow you to go to 5 and 7. At 5, maybe you can go between 1 to 2. At 7, maybe they allow you to go from -3 to 1. So you can go from here to here to here to here to here. Right? So that is the question. I mean, you may have other ways. So how do we think about this problem? As we mentioned before, the first step is always simplify. Right? Let's find something that we can solve easily. Okay. In this case, this is a little bit more difficult. How about what if A equals to B means I can only go to one place? That means, from 1, I can maybe go to 2. Maybe there's a ticket, another ticket allow me from 1 to go to 3, and 2, maybe I can go to 4, 3, I can go to 4, maybe 2, I can go to 5. So then this is our standard. So basically is our standard SSSP, right? Shortest path. So if I want to know the distance from every point to 1, I can go do the reverse, right? Standard trick. From checkpoint 1, I find the shortest distance to every checkpoint, right? That's our standard Dijkstra, right? Algorithm, right? Same for every point N. For point N, if I find every distance go to N, I can start from here. I can find the shortest distance from N to every point. Now, the only question becomes, how do I find shortest distance from every point, let's say X, to both 1 and N? So let's say from X to 1, it's like this, right? So there must be like a point Y, let's say before, from X to Y, they are all, we go to the same path. Then from Y, we split, right? We go to 1 and go to there. So obviously from Y to N, it is the shortest distance, right? From Y to 1 is, of course, also the shortest distance. From X to Y, of course, is also the shortest distance. Right? The only question is, how do I find Y? I mean, I can do it stupidly, I can search for every point and find what is this point, this distance plus this distance plus this distance. But I can do something smarter than that. Let's say, again, let's say we have 1, 2, 3, 4, 5, right? So how about I make a virtual point? Let's say virtual point equals 6, which is that point is you go to both 1 and n, right? So then the distance from each point to this virtual point is the shortest distance from 1, to 1 plus the shortest distance to n, right? So let's say the shortest, initially I find the shortest distance to 1, right? Let's call it this 0, okay, for each point, right? I find the shortest distance from each point to n. Let's call it this 1 for each point, right? Then here, the initial condition we can say is for each point to this virtual point, which is combination of 1 and n, is simply as I go to 1 plus I go to n, right? Okay, so I do so that's my initial condition for each point. Then for example, if I look at this point, what's the optimum condition? I can go from here to here, that's my initial, or maybe I can go from here to here, right? So this distance plus this distance may be smaller than this distance, or maybe ticket 2, checkpoint 2 can go here. Here, this plus this may be less than this. Again, that's our standard Dijkstra, right? So I can use Dijkstra to do this. Instead of doing, loop through every point, I can do OM, right? So now that means if I only go to one point, if it's a checkpoint have a ticket that can only go to one checkpoint, right? I know how to solve it. It's my standard Dijkstra. Now the question becomes, what if it's like this? Each ticket can go to multiple checkpoints. So let's think, right? So if I have, if I start from checkpoint 1, there may be a ticket, ticket X that goes from 1 to 5, for example. And this is, you can buy it from checkpoint 6, right? So that means I can go from 1 to checkpoint 6. Maybe there's another ticket, it goes from 1 to 10, for example. This is, you can buy it from checkpoint 7. I can go from 1 to checkpoint 7. So then this is, again, the same standard Dijkstra. The only thing you need to find out, the only thing you need to do is, if you think about Dijkstra, right, we need to find the equivalent of adjacent list, right? In Dijkstra, we do adjacent list to find one is connected to which. In this case, is how do we find these tickets, right? So of course, again, we can loop through every ticket, and that is n squared, right? That becomes n squared because every point you have to look at n times. But how do we each time we cannot do n, right? For each point, as n times. For each point, you cannot do n. You have to be able to use log n to find those tickets. How do we do that? We know segment tree, right, usually allow you to optimize from n to log n. So basically what we want to do is, for example, if we're searching ticket X, okay, I want to go down the tree to say, hey, let's say, there's bunch of segments, right, in the tree. Is X in this tree, in this segment, or is not in this segment, right? If X is in the segment, I will go down. If X is not in this segment, I'm not going down. So think about it, right? So if you look at this example above, we have 1 to 5 and 1 to 10. Our standard trick, right, is let's sort by the left-hand side first, right? For example, 1 to 5 is this my first leaf. For example, 1 to 10 is my second leaf. And let's say this one is, this ticket is 3 to 7. Let's say this ticket is 5 to 6, meaning this is my A and B, right? So if I build a segment tree, each leaf is my ticket, then I just need to know my left-hand side and my right-hand side, right? Basically is this, all the ticket underneath it can cover maximally what range. If my X is in the range, then I'm good. I'm going to search. If X is outside the range, I'm not going to search. Right? The range is easily defined. Right? This side is minimum of A. Right? This side is max of B. Right? So in this case, it's 1 and 10. In this case, for example, it's 3 and 7. Right? So then I can do this. Then the second thing we need to change in the dice is, right, we always use visited, right? We mark it. If we visit a site, I always mark it as a visited, right, equal to. In this case, what we need to do is we somehow need to make the tickets, right? We need to mark the tickets as visited. How do we do that in the segment tree? We can do it this way. For example, we want to mark this ticket as visited, not to use it anymore. How about, remember we minimum left and maximum right. How about we make the maximum is 0, right? So this become, when you do this search, right, you will, if you come down here, because the X is not going to be in the range, you're going to do it. When you do the pull up, when you do the standard pull up in a segment tree, this become updated to 1 to 5, right? For example, if this is visited. So that's how we can use this. We can do other things. We can use a flag, for example. We can also do a flag, right? Visited flag. And we can do that same thing and just do the pull up. But I think this probably is the easiest. So we just make it 0 because the maximum, right? We just use a maximum property. We can also do this. We can also make this infinity, for example. That's another way to do it. So that's the approach. Basically, what we do is, let's go back again. By looking at a simple case, okay, like this, we find out that we can use a standard dice structure, right? Do it 3 times. First, starting from 1, second, starting from n. The third time is we add a virtual point, right? And just update the initial distance. Then we can solve this. Then if we generalize it to tickets, then we just need to use instead of adjacent list, we use a segment tree. So we can search. Of course, remember we sort the ticket first. Right? We search for it, and then once we find those tickets, then we mark it and make it. We mark it and remove it from the future search. Okay, so that's the algorithm. Let's try to implement this. We're going to try to implement it as pseudocode. Right? I'm not going to write all the code, exact code, C++ code. Instead, we're going to use pseudocode and just explain how it works. And you guys, as a homework, need to go back and write the code. Right? So we need the tickets. Right? tickets need a checkpoint, and we need a price. Let's see, what is the price? 10 to the power of 9. I mean, just to be safe, let's make it long. Okay, price. And we need a checkpoint, 2 points, right, from A and B. We need to compare, right? We need to compare by A, right? Sorry. Right. We need to compare sorted by A. Okay. So we start by, right? We start by seeing, right? Seeing this for each ticket, right? For each tickets. I'm not going to do all the declare, variable declare, and all that stuff, right? For each ticket, we need to get in which checkpoint it is, what is price, right? What is AB range. Then we need to sort the tickets, right? Then we need to initialize the segment tree, right? So let's see how the segment tree should work. Ticket seg. Okay. And obviously, for each node, what do you need? For each node, you need minimum A and minimum A and max B, right? Okay, there is the initialize, right? So it's going to be standard initialize. You put each ticket on the leaf, then you do the pull up, which is, you do the pull up, which is a simple to the minimum of A and the max of B, right? Okay, so you initialize it. Then you do, remember, we do this, right? We find from point A, okay? So then we need to find this 0, right? Which is SSSB of starting from 1, right? So we need to find this one, which is starting from point A, okay? So let's write that. Okay. So you need the starting point, right? Which is my standard dash, right? Basically your first, let's say, initial distance, right? So make everything is infinity, right? Then you need a priority queue, right? In the priority queue, you need to, so let's say, if the starting point is 0, right? Then obviously the distance of 0 is your starting point. I mean, sorry, just checkpoint 1 is your starting point. If your starting point, starting point is your starting point, right? Then your priority queue, you have to push in everything that is not infinity distance, right? That's your starting point. Then you do the standard while priority queue, when the priority queue is not empty, right? Then you first obviously you pop out the top, right? Let's say this is the current point, right? Let's say, look at here. This is your current point X, right? So if if X is within the range, right? So if minimum A less than X and less equal max B, right? If it's this, then you go down, right? And of course, I need to do something. If it's leave, then you then you go, then actually, I was not doing it. Then you need to first find the leaves. I was trying to do two things on it. So let's say we need to find this list of things we're visiting. It's going to be my segment, let's say called update, right? Update point X. Okay. So it's going to be a list of things of the tickets. Right? So we need to implement that in here. It's update, which is the point I'm searching, right? In the tree, I start from 1, right? It's my left is 1, and my right is not the original n, right? Because in a segment tree, you have to be power of 2 to the power of something. Okay, so basically is if it's leaf, right? If leaf, which is L equal right, then you put this V into the ticket L into right? This thing you're going to return. And then if it's within range, right? If max X B, then you go down the tree, right? Else you don't, you don't do else you don't do anything. Actually, just and if you go, you also have to remember we have to mark this, right? We make the max, right? So then, of course, you have to do the pull up. Standard segment tree stuff. So then here you find the distance of this and distance of that. The next thing is you do this. Right? You do the virtual point. So let's call it distance 2. Okay. So virtual point of n plus 1. Okay. So now we need to say if it's n plus 1, then the distance then you have to update all of them, right? So it's this 0 of this thing, this 1 of this thing, right? Then after that, then you just see out. So that's basically how you do it. The P is basically this, right? How you update the segment tree, how you find which ticket, and how you update the segment tree. Okay. Oh, sorry, I did not finish this, but it's a standard, right? Once you find which one, which leaf, right here, which leaf is, you can do this tick. When you find the list of those tickets, right? Then for each ticket, right? For each ticket, let's call it T. For each ticket, you do the standard. You do the standard thing, right? Basically, if it's a smaller distance, then you update the distance, right? And then you push priority, right? So the standard dash chart stuff. So that's basically for today. Again, coming back to the ticket one, the first step to figure out the problem, as always, is try to find a simple case that you know how to solve. Then we know how to do SSSP. Then we try to generalize it. If you look at this, right? So we can easily find each ticket. The only trick is how do I make the search from n to log n? Then we use our standard segment tree approach and modify the texture a little bit, but it's basically the same texture. Again, thanks for everybody for coming in today for this problem. Next time, we will talk about the next question, problem number 2. See you until then.